Hello everyone! So I hope you are still okay there. This time I will be discussing these topics on DC electric circuits, Ohm's law, series connection and voltage division theorem, parallel connection and current division theorem, and Wye-Delta transformation of resistors. So also at the end I will be solving some of the problems from your assignments because I know some of the problems there will really crack your brains, but of course you are engineering students, so I should really expect some from you. So let's get started. Let's start with Ohm's law. So I will be just scanning some of the pages here because I know it's understandable for you. Ohm's law is just equal to V of equals, is just stating that V is equal to IR, and then power is equal to VI, or I squared R is equal to V squared over R. And for the notes there, I just want you to look at that. We will focus on how to solve we will focus here on how to solve worded problems about these topics. Applying Ohm's law, we have the direction of current by convention, because there is another direction of current which I will not be discussing to you anymore, but only this one. Conventional flow of current flows from the negative terminal to the positive terminal as shown in figure 1. This is an open circuit, which means the resistance here approaches infinity, and this is a short circuit where the resistance here approaches 0. And again, we will just discuss the basics since this is just a basic electrical engineering. Conductance, I will skip that. This problem, it's just direct substitution. Okay, so this part, what is a branch, what is a node, and what is a loop? So a branch is any two terminal element such as a voltage source or a resistor. So what is a branch? A branch is any two terminal. So for this one, this is the branch that we have. So this is one branch. Any two terminal element, be it an active source or a passive element, and this one is another element, that is another branch, and this is another branch, another branch, and another branch. But guys, if you have two branches that are in series, say this 10 volt element and the 5 ohm resistor, they are both in series, therefore this is considered as one branch. Okay, so for the node is the point of connection between two or more branches. For this one, actually we have many nodes, no? This one, this one, this one. Connection of two or more branches. This one, this one, and this one. But as it is said here, adjacent nodes that do not have an element in between, say for this one, this node and this node, there is no element in between of them. Therefore, those nodes are just considered as a single node. Wait. This is just considered as a single node. And for this one also, these adjacent nodes, there are no elements, passive or active elements in between them. Therefore, this is also considered a single node. Okay, so now what is a loop? A loop is any closed path in a circuit, any closed path. So for example, this one, this is a closed loop. This one, from this point to this point to this node to this node, and then to this node. A closed path, that is considered a single loop. And also this one. Okay, So from point C to B, to this point, and then to this point. That is also considered a single loop, and also this one. But do not limit yourself there. I can also have a loop which is this one, from this node and then up to this. Okay, so this is also considered a single loop. So that is for the branch, node, and loop. Those are just terms that you need to be familiar with. So, okay, let's proceed for the next part, the series connection and voltage division theorem. Series connection, when can you say that two elements are in series? The elements are connected in a way that they share one common node and no other element is connected on that common node. So for example, I have this resistor, this is his node, and the other node, the other one. So when can you say that they are series if they share one common node? Regardless of these other nodes, as long as this common node that they have, there is no other connection in that, it's alright. Even though I have here a resistor and then this one, I don't care about that one. And then on this node, I have a resistor here. Wait. I don't care. As long as there is no connection on their common node, then therefore they are in series. You need to be, you need to know how to determine series resistor so that when time comes that you will deal with complex circuit, you won't be deceived, okay? Or you won't get confused with the connections. So for this series connection, as you can see, the equivalent resistance or the total resistance across point AB is just the sum of the resistors, so that would be easy. And the voltage drop or the total voltage would be the sum of the voltage drops across R1 and R2. And then since this is series connection, the current that will pass through here, we can say as the total current, will also be the same as I1 and I2. Why? Because this is a series circuit. So whatever current or whatever electron flows onto this branch is just the same amount of electrons flowing onto this branch. That's why for a series connection, the current here is just the same as the current here. Now let's proceed to the next part. Voltage division theorem. This can be applied in a series circuit only. So it's like a shortcut in solving directly for the voltage drops across the resistors. So as you can see from the series connection here, you can't directly solve, you can only solve for V1 if you have the value for I1 and I2. And you can solve for V2 if you have the value for I2. But for voltage division theorem, I won't be showing you the derivation. Series circuit, you can directly solve for the voltage drops across this resistor, and you just use this formula. So take note, V1, that would be R1 here. V2, that would be R2 here. So later on, you will know why. So let's proceed to the next. So I will be making this quick and easy so that for other students who do not have a good internet connection at home or just using data, you can save as okay, so let's have this sample problem. A load of 10 ohms. So let us assume that we do not know the solution for this problem. We only know the problem itself. So we have here a load of 10 ohms was connected to a 12 volts battery. The current drawn was 1.18 amperes. What is the internal resistance of the battery? So you must know what a battery is. So a battery, any battery, even a battery that is connected or used for your alarm clocks, diba? They have terminals. Okay, and it is said here that this load is connected to that 12 volt battery. Therefore, the battery can supply up to 12 volts. No, and then the current drawn was 1.18 amperes. So you just need to be familiar with some of the terms by practicing. That's why I need you to practice, and that's why I'm giving you that very difficult questions in your assignment so that you won't be surprised during our quiz. So what is the internal resistance of the battery? Therefore, a battery has an internal resistance which is connected in series to that electromotive force. Now we have this circuit diagram. So as you can see, this is just simply a series circuit. Diba? But if you do not know what is a battery and you don't know how to connect the internal resistance, then you cannot really answer this simple circuit if you are not familiar with these terms. That's why I need you to practice. And with this given circuit, it will really be easy to solve for the internal resistance. With this solution, you have to solve for the total resistance because you have the total voltage and the total current. Now you can solve for RT, and we know that RT for a series circuit is just the sum of all the resistances. Then you can simply get for RI, which is the difference between this total resistance and the load resistance. Okay, if you want a break, then just pause the video, but I will continue right now. Parallel connection and current division theorem. A while ago, we discussed series connection and voltage division. So this is like the opposite of that topic. So parallel connection, the elements are connected in a way that they are connected to the same two nodes, even though other elements are connected to those nodes. So I have experienced that students are really assuming, okay, these two resistors are in parallel, although they are not. And these two resistors are in series, although they are not. So when can you say that they are parallel? So if you have here a resistor and another resistor, when can you say that they are parallel? If this is connected and this is connected, and we do not care if there are other connections there. I don't care if there are connections there. There are connections there. As long as both of their nodes are connected. For a series, we do not care about the other nodes and these nodes, as long as you do not touch this one. No touch. And this one, you may touch that as long as they are connected. You may touch that as long as they are connected. If only one node is connected and the other is not, then they are not parallel. So for this parallel connection, observe for the formula for the equivalent resistance across A and B. 1 over RT is equal to 1 over RA plus 1 over R2. But if you have only two resistors in parallel, so you can really simply this shortcut, not really shortcut, but a simpler way for solving RT. Ninduta, joke. VT is equal to the potential difference across R1 and R2. So if they are parallel, the voltage is just the same. And for IT, that would be the sum of the branch currents. Why? So if you are going to look at the diagram, the electrons flowing here, which is your source, must have been divided when it reached this node. So the electrons flowing here must have been divided across this node. That's why if you're going to add this one, it must be the sum, or it must be equal to the current here. That's why your total current for a parallel connection is the sum of the branch current. So it is like the opposite for series, because for series, Vt is the sum of V1 and V2, but IT is the same. But for parallel, Vt is equal to V1 and V2, while IT is the sum of I1 and I2. So how about for current division theorem? This can be applied in a parallel circuit. So voltage is for series, or voltage division theorem, or VDT, is for series connection. Current division theorem is for parallel connection, a parallel circuit. So for parallel circuit, you cannot directly solve for I1 and I2 unless you have V1 and V2. But because of current division theorem, you can directly solve for I1 and I2. So you need to observe for the difference in their formulas. Be careful. For current division, when you look for I1, take note of I1, this is R2. I2, R1. How about for voltage division theorem? What's that? So for V1, it's really R1. Okay? Take note of the subscripts. A simple mistake there would really make your solution wrong. Okay, series parallel. It's just simply the combination of series and parallel connection. So if you will be an expert to the series connection and an expert to parallel connection, so this won't really be a big problem to you. So let's proceed with problem solving. This is a simple one. We have 3 resistors, assuming that we do not know the solution. We're not seeing the solution right now. 3 resistors of 10, 12, and 15 ohms are connected in parallel. Evaluate the value of the current to the parallel system that will make the current in the 10 ohm resistor equal to 2 amperes. So the best way to solve this problem is first you understand the problem, and as much as possible translate it to vernacular language so that you can really understand it. If you are a Cebuano, then translate it to Bisaya. So after understanding the problem, as much as possible, if you can draw the diagram, then do so, so that you will have a better analysis of the problem. So for this one, the diagram is already shown, and it says here that at the 10 ohms there is a 2 ampere current that passes through it. And how would you solve for the current to the parallel system? So what is being asked here? So we are solving for the total current. And what are we going to do first? So do the analysis. So we have here 2 amperes and 10 ohms. We will get the voltage across this one. And once we know for the voltage at this branch, and since this is a parallel system, then we will know for the voltage on this branch and on this branch. And after that, we can get for the total current, because we can get for the current here and here, as what is shown on the solution. So that the total current will be equal to 5 amperes. Now how about this one? When two resistors RA and RB are connected in series, the total resistance is 36 ohms. If they are connected in parallel, total resistance is 8 ohms. What is the ratio of resistance RA to RB, assuming RA is greater than RB? So if they are in series, what will be the formula? Just add them. If they are in parallel, what is the formula? Do this one. So by getting RA and RB, so I assume that you have recalled your lessons from your algebra on how to solve for two equations with two unknowns. And I just do the shortcut, so we have here that RA is equal to 24 ohms. Why? Because there is an assumption here that RA is greater than RB. Then the ratio of RA to RB would be 2:1. Wye-Delta transformation of resistors. So actually, there are times that the resistors are connected neither in series nor in parallel. So, example for this drawing, if I'm going to ask you, is R1 and R2 in series or not? Although they share a common node, but there is another connection. Therefore, you cannot say that they are in series. Are they in parallel? Also no. Why? Because although these nodes are connected, these nodes are not. Okay? So, that's why they are connected not in series nor in parallel. How about this one? For RA and RB. Oh. Well, actually, it is assumed that on this drawing, there is a connection here. And there are also connections here and here. That's why for RA and RB, if they are in if you are asked if they are in series, not, because although they have a common node, there is also a connection here, and they are not in parallel also. Why? Because although the one of their nodes are connected, but the others are not. And of course, you can see why they are in delta and why they are in Y. They are in Y because they have the three of them share a common node, and they are in delta because they form like a delta. So actually, these transformations of Y connected resistors to delta and vice versa are used so that complex electrical circuits can be simplified. So when you do the transformation, after that transformation, we expect that we can do a simplification of resistors through the use of series or parallel formulas in solving for equivalent resistances. So if you are to transform Y connected resistors to delta, so what will be the formula? Okay, so the formula is here, and I think I put here a small note. To get for RA, so it is assumed that R1, R2, and R3 are given, and you are to transform them into this one. Therefore, the unknowns are RA, RB, and RC. And to get for RA, the denominator would be the opposite. Okay, so this is like RA, RB, and RC. So RA, when you solve for RA, the denominator would be R1. It's like the opposite of RA. When you solve for RB, what is the opposite for RB? That is opposite for RB. That is R2. And opposite for RC, that is R3. Okay, and then you do the memorization na lang. For delta to Y, so assuming that the given is a delta connected resistor and you are to transform them or convert them into Y connected resistors, you are to solve for R1, R2, and R3. So if this is like R1, this is like R2, and R3. So if you are to solve for R1, the numerator will be the product of the adjacent resistors, RB and RC. If you are to solve for R2, what will be the adjacent resistors? That would be RA and RC. And for R3, that would be RA and RB. Okay, and then you do the memorization for the other parts of the formula. So let's have an example. Oh, no, there is a small note here. So if you are to transform, if RA, B, and C are equal, therefore the three resistors in delta are equal, and vice versa, and also the three resistors in Y are equal also, and then you are to transform this delta connected into Y and then vice versa. So we have a relationship here that R delta is equal to 3RY. So for example, I have here 3 ohms, 3 ohms, and 3 ohms, and I want to convert this to Y. So it is said here, R delta equals 3RY. Therefore, the equivalent for this resistance is 1/3 of this one. Now, if you were to get for RY, that would be R delta divided by 3. Therefore, this would be 1 ohm na lang. 1 ohm and 1 ohm. Or, if this is given and you are to convert this into this one, it is said that if you are given a Y and you are to get for the delta, R delta equals 3RY. That's why, if you have here 1 ohm, your delta connected resistors would be 3, 3, and 3. Okay? So let's have another sample problem. No, that problem is found there. 3 resistors of 6 ohm resistance are connected in delta. Inside the delta, another 3 6 ohm resistors are connected in Y. Find its resistance between any two corners. Okay. So I have here a delta, 6 ohms. All of them are 6 ohms. And inside that is, or our Y connected resistors, also 6 ohms. And we need to get for the equivalent resistance across or between any two corners. This corner, or you can solve for this corner. This corner. So how would you do that? First, without expecting for a Y delta, as you can observe with the figure, if you are to solve for the equivalent resistance across these points, can you see a series connected resistors or delta connected? This is not series. Why? Because there is a connection here. Not series, they are not in parallel also because there is a connection here. So as you can see, you cannot see here a series connected resistors nor parallel connected resistors. So you cannot simplify using those formulas. That's why you need to do a conversion of Y into delta or delta into Y. It depends. So actually this can be solved in many ways, and my way is this one. I want to convert these Y connected resistors into delta. Okay, this Y connected resistors into delta. And what would be the resulting figure? So as you can see, guys, you need to be aware of the nodes. Okay, so let's say we have this one, Y to delta. No, this one, Y to delta. If you have here a Y, the delta connected resistors would be at these nodes. This node, and then to this node, and then to this node, and then to this node. But if you have a delta and you will transform it into Y, so just observe the nodes where you will put the resistors when you do the transformation. Okay, this point, and this point. And then there will be a common node in between of them. So let's go back to the problem. We have here a Y. So where will be the new resistors? It will be on this node, between that node and this node. So this is the new resistor R1, and the new resistor R2, and the new resistor R3. Okay. Now, after the conversion, what can you observe? Is the circuit simplified or not? Or can we simplify the circuit now or not? So as you can see, there are resistors now that are connected in parallel, right? Which is this one, and this one, and this one. So they are in parallel. But what will be the value for R1? Okay, since we are converting equally connected resistors which are connected in Y, and the value is 6 ohms, so what's the relationship? R delta equals 3 RY. RY is 6 ohms, therefore R delta is equal to 18 ohms. So this is 18 ohms, 18, 18. And what will happen next? I can simplify the circuit. 6 ohms in parallel with 18. What will be the new value? That would be Rx, which is 4.5 ohms. So this is the more simplified diagram from a while ago. Now, we have done the simplification. We are to solve for the equivalent resistance across RA and RB. What will we do next? So as you can observe, this is already in series. Why are they in series? Because there is no more connection here. Okay, there is no more connection there. That's why Rx here and this Rx also are in series. Okay, and after that, when they are in series, they are also in parallel with this another Rx. So that RAB is equal to 3 ohms. Okay, so let's continue. Let's solve some of the problems from your assignment. So I have chosen this one. We will solve this problem together. So I want you to be with me in answering this. Like just don't listen, but try to analyze also. So we have here a problem. A bulb rated 110 volts, 60 watts is connected to with another bulb rated 110 volts, 100 watts across 220 volts means. Calculate the resistance which should be joined in parallel with the first bulb so that both bulbs may take the rated power. Okay, first is you understand the problem. Then if you can draw, then draw the figure to make a better analysis. So I want to draw the problem. I have here a 110 volts, 60 watts bulb. This is 110 volts, 60 watts bulb. This is our load 1, or say this is our R1. It is connected with another bulb. So it's like a diagram in your house. 2 bulbs with different ratings. 110 volts. 110 volts and 100 watts. Say this is our R2. They are connected across. When you say across, it's like in parallel. 220 volts means that is a 220 volts means. So calculate the resistance which should be joined in parallel with the first bulb. So there will be a resistance that will be connected across bulb 1, and we do not know why, but it is said here, so that both bulbs may take the rated power. So let's call that as Rx. Now you have drawn the problem. You have understood the problem, you have drawn the problem. What are we going to do next? So it is said here that both bulbs must take the rated power. So given this figure, what can you do to solve for Rx? So you need to recall all the formulas and the concepts that you know to solve for Rx. So what to do? It is said that this is 110 volts, 60 watts, and this is 110 volts, 100 watts. When they are connected in series, since we have here Rx that is to be connected in parallel, therefore, if we are going to leave that, like there is no Rx, like there is no this one, if this is only the diagram, then therefore they cannot take their rated power. That's why we need to put Rx. So what am I going to do next? In this figure, I know that this bulb is rated 110 volts, 60 watts. Therefore, I can get for the resistance of R1. What's the formula for P? If given voltage and resistance, that would be V squared over R. Therefore, R1 is V squared over P. So please recall that one. This will be 110 squared over 60. I'm sure that R1 is equal to this is 202 ohms. How about for R2? The resistance is fixed, guys. The resistance is fixed. Powers can be changed. That's why I'm solving for the resistance here, because I know this will not change. The resistance will not change, but since they are connected in series, therefore, if we are going to leave that there, this will change. That's why we are adding in Rx, so that they may take their rated power. R2 is V, let's call that V1. V2 squared over P2, P1. This would be 110 squared over 100. And this is equal to 121 ohms. Now that I have R1 and R2 and I do not know and I'm sure that this must be 60 watts and this is also 100 watts. So what can I do to solve for Rx? What's my next step? Can you do the analysis? So guys, are you with me? Since this is 121 ohms, 110 volts, 100 watts, and there is no change in here because R2 will take its power, that is 100 watts and 110 volts. Therefore, I can get for the current here. And if I can get for the current here, that will be like the total current for the system. Okay? Understand that if I can get for the current here, since this is like a series, okay? This is a series branch. Therefore, I can get for the total current. And if I can get for the total current, I can get for the total resistance across those points. And I know what is the total resistance given this diagram of resistors. So I can get for Rx because I have R1 and the value of R1 and R2. So I will get for I2, which is equal to IT that is I2, which is just equal to IT. That is P2 over V2, although there are lots of formulas to solve for I2. 100 over 110, and that is equal to 0.909. Now I can get 4 RT, which is equal to VT over I2, or IT, but IT and I2 is just the same. 220 over 0.909, and this is equal to 242. And what will be RT if you're going to look at this diagram? So RT is the parallel of R1 and Rx in series with R2, right? So I know RT is equal to R2 plus the parallel combination of, this is the symbol for parallel, okay, R1 and Rx. So R1 in parallel with Rx, that is equal to 242 RT minus R2. 242 minus 121, that is equal to 121. And then parallel formula, I know that R1 is 202, so I'll just do the shortcut. Please do the math in your calculator there. Rx will be equal to 302.5 ohms. Okay, and as I solve this problem, I've seen a shortcut that R2, for this to be 110 volts and 110 volts, R2 must be equal to the parallel combination of R1 and Rx. So let's proceed to the next problem. I hope you're still with me. If you want a break, you can really pause and go back when you are ready. Let's solve this next problem. In the figure shown below, if all the resistances are of 6 ohms, calculate the equivalent resistance between any two diagonal points. So first, observe the figure. Calculate between any two diagonal points between XY or PQ. But since this is really a complex circuit, try to simplify, or you could really modify if you can see that this is really a simple diagram. So the technique there is to label nodes. Okay, so let's say I have here a node X. Node X. From your node X, there is a resistor connected to node Q, right? So I'm going to draw there. I'm going to draw there a resistor towards node Q. And then there is also another resistor from node X connected to node Y, another 6 ohms. Okay, from node X, there is another 6 ohm resistor there connected to node Y. And then there is also another resistor from node X to node P. So from node X to node P. So we are done with this one. We are done with the connections from node X. Let's proceed with the connections from node Q. So from node Q, there is a resistor connected to node X, and we have already drawn that. To node P. Oh, okay. So there is a connection from node P to node Q. No. Oops. So what I'll be doing na lang is I'm going to extend P and Q. Okay, I'm going to extend P and Q so that I can draw a resistor between them. Right? This is the resistor in between the two nodes. And also, where are we? From node P, no? And there, no, node Q. Node Q to node, bale. This is node Q. And this is node P. Then there is a resistor there. And then from node Q, there is also a resistor towards node Y. Right, we're done with this one, and we are now at this one. So there is a resistor there. We are done with the connections from node Q. We'll proceed with the connections from node P. Node P to node X, we are done with that one. This is that resistor. Node P to node Q, we are done with that one. This node, this resistor. And node P to node Y. Okay, so there is a resistor from node P to node Y. Now we are done with the node P. Let's proceed with node Y. There is node Y to node X. We are done with that one. Node Y to node Q. We are done with that one. And node Y to node P. And we are also done with that one. Therefore, we have drawn the resistors. Check how many resistors? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So therefore, this is the another form of that diagram, which, as we can see, we can analyze this in a better way when we have redrawn this circuit diagram. So the problem is asking for the equivalent resistance between any two diagonal points, XY or PQ. Okay, from this diagram, of course, I will choose the PQ. So I will ask for the resistance across both that point. Now, what to do? Can you see a series parallel? So that is really the first step. Looking for a series connected resistor or parallel and then combine them. So as you can see, there are none. But we can see a lot of Y and a lot of delta. Take note, guys, this is also Y connected resistors. This one, this one, this one. I'm just telling you. So now, what are we going to transform so that we can simplify the diagram? For me, I would choose these Y connected resistors. This one. And that one. And then transform that into delta. So that I will have a resistor here, a resistor here, and a resistor here. Because I know if this will be gone and we will have these resistors, I can see that this resistor here is in parallel with this one. And this resistor, I'm doing this in advance. And this resistor here is also in parallel with this one. So, what will be the next diagram? So, drawing again, it will look like this. This is Q, X, We have here a resistor from your node X to node Q. From your node X, we also have node Y will be gone, guys. This resistor, this is that resistor, and then of course that will not be lost. And they are connected to node P. And the node P to node Q, there are also two resistors present. So as you can see you see a more simplified diagram? Yes, we can see a parallel connected resistor. These resistors, they are in parallel. They are in parallel and they are in parallel. And as you can see, after that, they are in parallel, and both of these resistors will be in series and then in parallel with this one. So, looking at this diagram, actually, this is just the same as this problem. Diba? Parallel, and after that, series, then in parallel. So, I won't be solving that anymore up to that point because the video is too long. But I will just show you the values of the resistors. So, this is 6 ohms, right? 6, 6, and 6. How about the red? Resistors in red. Assuming that this is also 6 and 6 and 6. Ry converted into delta, since they are all equal, then this resistor is times 3. R delta equals 3 Ry. Therefore, this is 18 ohms. This is 6 and this is 18. 6, 18. It is really similar. I think it's really similar with this one. Diba? It's similar to that one. So the answer is, what's the answer for this problem? 3 ohms. So I won't be solving anymore manually, but we know that our QP, just refer to our sample problem, our QP is equal to 3 ohms. So thank you for taking your time listening to me, and I hope you enjoy your day. Bye!